Just okay. So good morning, everyone. Good morning to all the participants present here as well as watching us on YouTube. We are here with another technical session on control system and Coppeliasim, where we have team members from e-Yantra joined with us who will be taking the session. Abhijit Pandey sir, Kruthat as well as Jarish, and yeah. So let's we are late on time, so we'll just directly dive into the session. So over to you, Abhijit sir.
Thank you, Ruchi. So I'll share just a second. I'll share my screen and I'll probably turn off my video because might be consuming bandwidth. Okay. Okay, I think I'm audible. Just give me a quick confirmation. I'm audible?
Yeah, yes, sir.
Okay. Okay, good morning, everyone. Welcome to, somebody said no in chat. From my side, my team is able to hear me, so I'll just go ahead with that. Okay. So good morning, everyone. My name is Avjit Pandey. With me, I have Jerish and Kurtat as my support team, and we will be today we'll be talking about uh, how we are implementing control system and creating a self-balancing robot using two techniques. One is PID controller and LQR controller. Uh, can just someone quickly confirm if the audio level is okay, or do I need to speak up?
Fine.
Audio is fine. Quality
It's
is
fine.
graded okay. Okay, good. Okay, good. So let's jump into the discussion. So we'll first look at two types of self-balancing, two-wheel self-balancing robots that we have built so far at eYantra. And then we'll learn about PID control technique. Then we'll learn about state space modeling and mathematical modeling and what are the steps to follow. Then we'll learn about linearization, stability, stabilizability, and how discretization is done for a continuous time system. Then we'll also learn how LQR control technique is implemented and its elements like weight metrics like Q and R. Then we'll also talk about the hardwares that we have used to create our own two-wheel self-balancing robot. So let's dive into the first topic. So there are we have designed over the period we have designed two types of self-balancing robot. One in which the wheels are side by side. I'll show you an example of it. It is from the biped petrol theme. I'll just play the video. So here you can see that it's a two-wheeled self-balancing robot. Wheels are on the left and right side, and it is moving forward and backward. And using differential drive between two wheels, it's also able to change its direction. So the motion of the wheel and the balancing action both are in the same direction. And this is what is going to be the center of discussion for today's session. Apart from that, we have also developed one more robot, which is called delivery bike or dairy bike. We had two editions of it. It's a bit different from this robot under discussion. Let's see one example of the delivery bike. Here you can see it is also a two-wheeled self-balancing robot, but wheels are in front of each other, in front and behind of each other, and the balancing action is done using a reaction wheel. A reaction wheel is a flywheel mechanism which rotates clockwise and counterclockwise to provide the counter torque for keeping the system in the upright position, which is the unstable equilibrium position. You can see these videos in the eLSI channel. Let's move forward from this. So we had one theme based on this reaction wheel based self balancing bike last year. Okay, moving on. So I'll hand over the floor to Jerish to talk about PID control technique.
So I hope I'm audible. Can anyone confirm? Yeah, okay, fine. So let me share my screen. Yeah, the screen is visible. Okay. Now we are going to learn about PID control technique. So before diving into the PID control technique, let's know about the flow diagram that's shown here. So you can see the block named as planned or process. So it's nothing but a system. So in our case, it might be a bot, right? So for the bot, we are giving an input which is termed as u of t. You can see over here, and the plan gives us an output which is y of t. And here we are seeing like r of t, which is nothing but the desired output that we need to get from the plan, basically. So you are taking the difference of the desired output of the plan to the output of the plan. That's nothing but the y of t. So that is nothing but error, which we are representing as e of t. So this error is given to the controller. In our case, it's a PID controller. So which is having PI and D term, which I will be covering in a within few minutes. And this PID controller will give us an output which is u of t and which is fed to the plant as an input, right? So now we can see about what is this PI and D controller mean. So PID stands for proportional, integral, and derivative controller. So first, proportional controller. So proportional control is having a term like proportional gain, which is nothing but the KP that you are seeing here, and error. So what this proportional controller will do is like it will give an output which is proportional to the error. For example, if the error is high, it will give an output which is high, and if it's low, it basically gives a output low. So basically, it makes us to achieve the set point based on the error that we are getting from the reference value and the actual output that we are received from the plan. So due to this, due to the inertia of the system, we might be there might be an overshoot caused due to the proportional controller. So it will be oscillating about the set point for so long. So in order to overcome that uh, overshoot that is caused by the proportional controller, we will be using a derivative controller. So derivative controller is the controller which is having a derivative gain which is represented as KD, and it's having a derivative of the error. So in physical terms, derivative of the error is nothing but the difference between current error and the previous error. So it's basically like knowing predicting the immediate future of the system behavior. So the system behavior can be determined, like futures can be determined by the derivative controller. So based on that, whether the error is going to be increase or ascend or descend can be predicted by the derivative controller, and it can be controlled using the derivative part. So PD controller can be used for like so it will basically reduces the overshoot. So even oscillation, and ultimately it will be reduce the oscillation and it will try to maintain in the set point. So in some cases, even though we are applying the P and D, it might not be able to reach the set point. So in that case, the integral plays a very major role. So integral, what's the integral? It's like a summing up of the all the error that we have faced so far. So it will basically lift the system output to the desired value. So we can just see how it works in a more intuitive manner. Okay, sorry, I forgot to mention about a steady. There is a steady, like I've told you, like sometimes there might be the output might not reach the set point, so which we call it as a steady state error. So this integral value will eliminate the steady state error that we are facing. Fine. So now we are going to look on to how intuitively the PID controller works. So I hope you can see the screen. Okay, no. Uh, I hope the screen is visible. Okay, fine. First, what we are going to do is like we are going to give a proportional gain. So let's see what is happening. So as the proportional gain increases, you can see there is an oscillation, right? So there are so many oscillation, right? So what I've told, in order to avoid like reduce the oscillation, we'll be using the derivative term. Now let's see what the derivative term do. Now you can see the oscillation has been eliminated, right? So, and I've told you about the steady state error that's caused due to the PD controller. So you can see this is our set point. The dotted lines are our set points, and this is the output that we have received. So we must elevate this output to the our set point. So this will be taken care of our integral controller. So let's see what the integral controller does. So can you see it's moving towards the set point? If I'm okay, fine. Now you can see it's reached the set point. So this is how the PID controller works. So now I would like to hand over the session back to Avijit sir.
Okay, so we have seen how PID controller can easily create a system and we can use it to control a plant. But here there is a problem in this scenario is that we the whole plant acts as a black box. We don't know what is the intricate nature of the plant. So in order to better control the plant and have better control over the states, we needed something better. We needed a different controller, and for that we opted for LQR controller. But the requirements for LQR controller is that we need to have a state space model in place for the plant. So let's look at how we can derive a mathematical model for the plant. I'll share. Yeah. Hmm. So in general, a state space representation can be shown for a continuous time invariant linear system as x dot is equal to ax plus bu and y equal to cx plus du, where A and B metrics are where A is representing the relationship between the state, that is x, and the rate of change of state x dot, and B is there for u, that is input, and rate of change of state x dot. Further, so in order to have these equations ax plus bu and cx plus du, we need to derive a mathematical model of our system. and that can be done by following these steps. So the first step we need to find, we need to do. So this is a, there are various methods to do it. This is the common method that we acquire at eYantra. So we are sharing it with you. So the first step is to find the kinetic energy and potential energy of the system. Then we'll find the Lagrangian function, that is L equal to kinetic energy minus potential energy. This will help us getting into the equation of the system. And before moving further, we'll also need to calculate the Euler-Lagrange equation, which is represented as d by dt of del L by del Q dot minus del L by del Q is equal to F, where Q and Q dots are simply, Q is the state of the system and Q dot is the rate of change of state of the system. And it is equated to F, where F is non-constraint force. In our case, it will be the torque of the motor that is used to balance the system. Further, we will solve this Euler-Lagrange equation, and we will try to find the equilibrium point of the system. So we'll have the equation of the system, we'll try to find the equilibrium point of the system. So to find the equilibrium point, we will equate the rate of change of states to 0. So why we do that? Because if you think about the self-balancing robot, let me turn on my camera. Not only self-balancing robot, if you think about any stable system, if it is stable, it will reach at a point where all the states become constant. Since all the states are becoming constant, the rate of change of states will become 0. So for example, let us suspend this as a pendulum. So this is a stable situation, and because of this, not any state is changing, neither the angle of the wheel nor the angle of the board. Okay, so when system is in equilibrium, the rate of change of uh, rate of change of states becomes 0. Okay, so once we find the equilibrium point, we'll linearize our system, the equation systems, uh, by doing Jacobians around the equilibrium points, and this will give us the A and B matrix of the system. So let's take a example, hands-on example of how we can calculate all this. I think it's visible. Is it visible? Yeah. Okay. So here we can see that we can represent our system like a wheel and a mass mounted on it through a pole. Okay, and the length of the pole is LC, and mass of the center of mass of the system is MC, and the radius of the wheel is RW. Okay, so if the system is falling and wheel is rotating, we will reach from this state to this state. And if we track the change of coordinate of center of mass is equal to, so suppose this whole robot is moving in XZ plane like this. Okay, so in this situation, why we will have the x coordinate of the center of mass change to RW theta W L sine theta C, that is this displacement plus this displacement. This displacement is according to the radius of the wheel and rotation angle of the wheel. So wheel rotated by theta W degree, and the whole system displaced by RW theta W, and beyond that the bot also tilted. That's why the center of mass also moved with LC sine theta C by the length by the displacement of LC sine theta C, where LC is this length. Okay. Similarly, for wheel also, the one more thing, here we are assuming that the center of the wheel is the origin 0, 0, 0. Okay. So in this situation, when the bot moves, the wheel rotates by theta w dot theta w degree, and the displacement is displacement of wheel is rw theta w, and it's not moving in z direction. Okay, because it's at the bottom of the system. Now we can further convert these displacement matrix into velocity matrix by simply doing x dot z xc dot zc dot xw dot and z xw dot and zw dot, and we'll find these. This is the outcome. Using these matrices, we will be able to calculate the velocity of the system, means both velocity of the wheel and center of mass. Why are we calculating velocity of the wheel and center of mass? Because we want to calculate kinetic energy and potential energy also, because we want to do Euler Lagrange. We want to do we want to find Lagrangian function. Okay. So using this VC square and VW square, you can at any point during this presentation, you are free to take screenshot and do derivations in detail at your own end. We will cut some steps in between. Okay. So if we look at the Lagrangian function, we have seen Lagrangian function is equal to L is represented as L is equal to kinetic energy minus potential energy. So here we will have kinetic energy of the bot center of mass minus potential energy of center of mass plus kinetic energy of the wheel minus potential energy of the wheel. Also, since we have two wheels, it will be also multiplied by 2. Here we can see, since the wheel is not moving in z direction and it is at the origin, we'll have the PEW as 0. So if we put all the values of KEC, PEC and KEW into this equation, we will reach to this underlined equation. Okay. Here is an expanded version of it. So once we have calculated L, we will move on to calculate the Euler-Lagrange equation. So if you remember, Euler-Lagrange equation is stated as d by dt of del L by del Q dot or del X dot minus del L by del Q is equal to F. So what things we need to calculate? We need to calculate del L by del Q and del L by del Q dot, and further d by dt of del L by del Q dot. Okay. So how do we do that? Using this equation, the Lagrangian function, we do partial differentiation by like this del L by del theta W. First of all, what are the states in our system? States in our system is theta of the body, angle of the body, rate of change of angle of the body, angle of the wheel, and rate of change of the angle of the wheel. Theta, theta W, theta W dot, theta C dot. Okay. So here we have del L by del theta W. Then we'll calculate del L by del theta C. We calculated del L by del theta W dot, del L by del theta C dot, and then further we did time derivative of equation number 3 and 4, and we got equation number 5 and 6. So using equation number 5, 6, 1 and 2, we will find two Euler-Lagrange equations like this. So you can see d by dt of del L by del theta W dot minus del L by del theta W is equal to T1, and d by dt of del by del theta c dot minus del L by del theta c is equal to T2. Okay. So since we have the Euler-Lagrange equation, we will move on to next step. Yeah. So we have these two equations. What we will do, we'll put equation 5, 6 and 1, 2 into these two equations. And what we will try to do, we'll try to bring everything on one side and theta w dot, theta w double dot and theta c double dot on one side. So by doing that, we will be able to convert these two equations into these two equations. So here you can see the theta w double dot is depending on few things: T1, which is the input, T2, which is the second input, T1, T2, theta c dot, theta c. Yeah, that's it. And same thing is for theta c double dot. It is depending on T2, it is depending on T1, it is depending on theta c, and it is depending on theta c dot. However, you might notice that none of them are depending on theta w. Okay. Any doubt? No. No one will be able to respond. Okay, fine. So you might also be noticing that there are several K1 terms like K1, K2, K3, K4. So what we have done is here is that these equations are fairly large, but a lot of them are a big part of them are constants. For example, take example of this. It is a constant parameter. It is moment of inertia plus MCLC square. These are constants. MCLC RW. These are constants. So what we have done, we have grouped certain constants into different groups, and we have created new constants called K1, K2, K3, K4. These are like this. So if you are enthusiastic in playing with math, feel free to put equation number 1, 2, 5 and 6 into these two equations and try to derive this, try to reach these new equations. Okay, about these new equations of theta w double dot and theta c double dot. Moving on. So once we have these two equations are actually representing the actual system, but this is non-linear equation, and our controller is linear in nature. So we'll have to linearize it. But before we linearize it, we'll have to find the equilibrium point. So what I mentioned in the previous slides, that at equilibrium, the rate of change of state is 0. So x dot becomes 0. So so I have told that x, that means the states are theta w, theta c, theta w dot and theta c dot. So if this is x, then what is the x dot? It will be theta w dot, theta c dot, theta w double dot, theta c double dot. And this is going to be 0 at equilibrium. That means at equilibrium, we'll have theta w dot equal to 0, theta c dot equal to 0, theta w double dot equal to 0. Okay. Okay. Somebody is asking what is theta dot and theta double dot. Okay. Uh, So I'll show you, in fact. If you look at the camera for a few minutes, I have to unshare, no? How do I stop sharing? Okay, I think it's visible now. So see, this is our system. Okay, you look at like this is our system. So what parameters of this system we want to calculate? We don't want it to tilt. So if it is tilting, if it is at this angle, it is unstable. So we want to keep it upright. Okay, so this is the angle of the body. Okay, so we want to keep control of angle of the body. So that is theta c, theta of center of mass. So we want to not only control theta c, we also want to control the rate of change of theta c, because we don't want it to fall. See, falling is an action. There's velocity in it. So you don't want it to fall. So we also want to have a control over the rate of change of theta c. That is rate of change of falling of the robot. Okay, that is rate of change of theta c. That is called theta c dot. Okay, time derivative. Same thing is for wheel. So in this system, wheel and the rest of systems are two separate parts, and they are joined with each other through motor. So we also want to control the angle of the wheel, which is called theta w, and rate of change of angle of the wheel, that is called theta w dot. Is that clear? Okay, yeah. So go back to yeah. So since we are trying to so at equilibrium, at equilibrium, you as you have just understood, what are these are states: theta w, theta of wheel, theta w dot, rate of change of the speed of theta of the wheel, theta c, that is angle of the body, and theta c dot, that is rate of change of angle of body. These are our states. Okay, so at equilibrium point, rate of change of state becomes 0. Okay, that means x dot, x is the state matrix. Sorry, this one, x is the state matrix, where the order of matrices are order of states are theta w, theta c, theta w dot, theta c dot. So at equilibrium point, x dot will become 0. Okay, so that means we have got theta w dot equal to 0, theta c dot equal to 0, theta w double dot equal to 0, and theta c double dot equal to 0. Double dot means acceleration. Okay, dot, when dot is there, that means time derivative. But we don't know what is the value of theta w and what is the value of theta c at equilibrium. These values are all at equilibrium. Okay, so what we will do, we will put this system equation into this condition. So what we will do, we will put theta w double dot equal to 0, theta c dot equal to 0, and theta c double dot equal to 0, and theta c dot equal to 0. Okay, Acha, there's one more thing. At equilibrium, once the system has, in our situation, once the system has achieved the equilibrium, we don't want to disturb it. So when the system achieves equilibrium, the inputs will also become 0, because there will be no input, otherwise system will be disturbed. So at equilibrium, T1 and T2 will also become 0. So coming back to this, T1 and T2 will also become 0. So what will happen if we put all these values into and feed them into these two equations? What we will get? We will get sine 2 theta c equal to 0. That means eventually we have theta c equal to n pi, and in our condition n pi will take two values, 0 and pi. Okay, also you can see, since these equations are not depending on theta w at all, any angle of the wheel, at any angle of the wheel, we can achieve the equilibrium point. So for our instance, we'll keep it as 0. Okay, so combining these two, we have two set of equilibriums. Okay, one is where theta w equal to 0, theta c equal to 0, theta w dot equal to 0, theta c dot equal to 0, and another one is theta w equal to 0, theta c equal to pi, theta w dot equal to 0, and theta c dot equal to 0. So what does this mean? If you look at camera for a minute. So this is our upright situation and this is 0 degree. So theta c equal to 0, theta c dot equal to 0, theta wheel equal to 0, theta wheel dot equal to 0. And this is our second condition, second equilibrium point where theta c dot equal to 0, but theta c is equal to pi, complete 180 degree. And theta wheel dot are 0. Now, I have a question. You might be able to intuitively answer it. In which of these the system is default stable? So what does stable means? If I do not in which of these, so both of these are equilibrium points. Equilibrium points means if the system attains these value of states, it will remain there unless any external disturbance is given. Okay, so these are equilibrium points. So which one of them is stable equilibrium, which one of them is unstable equilibrium? So basically there are two types of equilibrium. One is stable equilibrium, one is unstable equilibrium. In stable equilibrium, if I give a perturbation, let's say this is the pendulum. So if it is hanging like this, if it is stable equilibrium, if I give any perturbation, it will come back to its original state. However, in case of unstable equilibrium, like inverted pendulum, if I give perturbation, it will move away from it. Okay. So there are two types of equilibrium points. So we have just calculated two equilibriums. Let's see. So one of them is stable equilibrium, one of them is unstable equilibrium. So this one is the unstable equilibrium, this one is stable equilibrium. Okay. Moving on. So what we have received, what we have figured out till now, we have calculated the system equations, two sets of equation which can represent our system in non-linear way, and we have also calculated the equilibrium points. Okay. Now, from these equilibrium point, we will try to calculate the state matrix. Okay. So in order to get the state matrix, that is the linear state space representation of the system, what we will need to do within these equations, we will take Jacobians, and those Jacobians will be taken around the equilibrium points, that is 0, 0, 0, 0. Okay. And with that, we will arrive at the final matrix. Yeah. And these matrix will be our A and B matrix, A, B, C, and D. So if we look at this, while taking Jacobians, we are doing partial differentiation of the theta w dot double dot and theta c double dot with respect to the states. Okay. These are partial differentiations, partial derivatives. And same thing we are going with respect to inputs also. Okay. And in fact, these are our state matrix. At the same time, we have y equal to c x, this is x, also x, this is u, cx du. Okay, so since our output is same as the states, we have C as a identity matrix, and since there is no feed forward, D is a null matrix. Okay, so if we I again give you an assignment, you do you take screenshot of this and try to calculate the x, the A and B matrix at your own end after the workshop. So once we calculate these, we will find that A and B matrix will turn out like this. Okay. Now, since there's a coupling, since wheel and the body are coupled through the motor, here we have T2 equal to minus T1. So this same equation can be further simplified like this. And this will be our final A-B matrix representing x dot equal to AX plus BU. So now we have, what do we have here? We have a linear state space representation of our non-linear system. Okay. Moving on. I will have to share. If any question is there, you can put it in the chat. Okay. So what we did so far, we took the kinetic energy and potential energy of the system, calculated the Lagrangian function, calculated the Euler-Lagrange equation. Then we also calculate, then we tried to calculate equilibrium point by putting the x dot equal to 0. That means the rate of change of state is equal to 0. And after that, we linearize the whole thing around the equilibrium point. Why do we linearize around equilibrium point? We believe that in a very narrow ball of very narrow range of the equilibrium point, the system behaves linearly. Okay. Then we substituted those linearized Jacobians into A and B matrix. Okay. Now, so we have a set of equations who represent our system around the equilibrium point. Now we have to find whether, now we can find other properties of the system. Do you want to talk about this? Okay. So I'll pass on the floor in a minute. He will show something about Octave. Okay. So coming back to, so now we have a system matrix A. Now what we can do, we can find different properties of this matrix A and find whether our system is stable, unstable, stabilizing, what is the stabilizability, what is the controllability, all these parameters. Okay. So if the eigenvalues of system matrix A lies within the negative half, left half of the complex plane, it is a stable system. But if any of it goes to right, if it lies to right, it is unstable. And sometimes if it is lying on the eigenvalues are lying on the vertical axis, then it can also be stated as marginally stable. Okay. And if system is unstable, if system can be unstable, but it's important that it needs to be controllable. So unstable system can be controllable. Okay. So we can that represents that we can design a controller which will be able to control the state of the system. Okay. So control controllability of the system is calculated through a controllability matrix. This matrix is represented presented as C. Oh, it is not there. Okay, I'll have to share again. So there's something called controllability matrix. So once you calculate the A and B matrix of any system, you can easily check whether it is a controllable matrix or not. So this controllability matrix is stated as C is equal to B A B, right? B A B A square B up to A n minus B, where n is the order of the A matrix. Okay. And this controllability matrix, if the rank of this controllability matrix is equal to the n, then it is a controllable system. Okay. वर्कशॉप चल रही है, हाथ में देना, रख दी. Okay, so now we have figured out how to calculate the state matrix and how to check whether the system is controllable or not. Now we are going to design the controller. So before we design the controller, we also need to understand that the controller that we are going to implement is executing within a discrete system, that is microcontroller. It's a discrete system. It's not a continuous system. Okay, it's a digital system. So what we need to do is we also need to convert our A, B, C, D matrix, which is in continuous time, to discrete time. Okay, so this is called discretization process. So in Octave or Matlab software, you can easily use C to D converter to convert ABCD matrix into their discrete version. Okay. However, at this situation, in this situation, you will also need to determine the sampling time of this system. Okay. So sampling time, all of us know, is the time period at which the sample from the sensor is collected, and it is in control of the user. Through coding, you can set your sampling time, and the same sampling time is used to calculate the ABCD discrete version of the ABCD matrix. Now, for the discrete version of ABCD matrix, the eigenvalues should, for stable system, the eigenvalue should lie within the unity circle of the Z space, right? Okay. So now we are going to implement the LQR controller. So we have, so as we can clearly see that in order to implement LQR controller, we need to have a state space representation of the system. Why is it called LQR? It is linear quadratic regulator controller. Why linear? Because we have the system of equations and in linear form. Our system is linearized. Okay, our equations are linear. Why quadratic? The cost function that we are trying to reduce is in quadratic nature. You can see here x transpose qx and u transpose ru represent they both, if you expand them, they both will yield a set of quadratic equation. Okay, set of quadratic equation. Now this is a okay. Now you can see two new terms here, q and r. So q and r are before that, it's a why this is called a regulator, because here we want to make all the states, all the variable of the system go to 0. So that is called a regulator problem. That's why linear quadratic regulator. Okay. There's also another type of problem. It's called servo problem, where we try to track the variables instead of making it 0. Okay. So we are trying to minimize this cost function. And within this, the Q matrix and R matrix, let's talk about them. The Q matrix is known as the X transpose QX is known as the error cost. This is the cost function. Okay, this cost function is what we are trying to minimize. Okay, so in that within that cost function, X transpose QX is the error cost, and U transpose RU is the energy cost. So there's a very deep meaning behind these. Let me put on the system again. Okay. So Q matrix is actually a diagonal matrix where Q1, Q2, Q3, Q4 in our case. Okay. And R here in our case is equal to, it's a scalar value as 1. So you might, if you remember, Q is X transpose QX is the error cost. So this shows in which state I want to minimize the error the most. Okay. And U transpose RU represents the energy cost. That means for through the R matrix, we tell that for which input we have how much energy is allocated, right? Yeah. And since in our case we have only one input, that is T, so we'll keep R as 1. Now let's look at Q matrix. So it is like that. This is not Q matrix, right? Yeah. Theta C, theta W dot, theta C dot. That means Q1 corresponds to theta W and Q2 corresponds to theta C, Q3 corresponds to theta W dot, and Q4 corresponds to theta C dot. Okay. So what does this represent? The higher the weight of Q1, the diagonal element of corresponding Q matrix, the higher the restriction will be put on that state. What does that mean? I'll give you an example. So suppose if our Q matrix is like 1000, 0, 0, 0, 100, 0, 0, 0, 0, 1, 0, 0, 0, 10. So in this situation, the corresponding value of theta W has the highest weight. That means the controller will try to restrict the change in theta W the most. Okay, it will pose the maximum restriction on theta W, and further theta C will be beyond after that. That means through these weights, we tell the system that which of these states are dearest to me, which of these states I want to keep constant, to keep it to the reference value, the 0. Okay. So if you think critically, you will see. Let's look at the camera now. So if you think carefully, in our system, what is the most important situation? What is the most important parameter? That is the angle of the body. Because once the angle of the body changes, it will start falling. So we don't want the theta C to change at all. So that is the most important parameter. After that, theta C dot. So we want to keep maximum restriction on theta c and theta c dot. After that, at third, we have theta wheel. So if theta dot of wheel. So if theta dot of wheel is very loose, that means robot will move forward and backward a lot. So we want to keep the bot stable at one point and keep it balanced. So we want to put restriction on angle of the body, rate of change of angle of the body, and rate of change of angle of the wheel. And angle of the wheel is least favorite to us. So if by that logic, coming back to drawing board again. So by that logic, our Q matrix will look like something like this. So we let's say this is theta C, theta W dot, theta C dot. So what theta W will be the least favorite. So what is the most favorite? Theta C. We'll put that as, let's say, 1000. Theta W dot, third favorite. So after theta C, most favorite is theta C dot. Then theta W dot. And then theta W. So this will be our. So by this logic, we are telling that this state is top priority. After that, this state. After that, this state. After that, this state. And this is represented by the size of the weight allotted to the corresponding diagonal element of the Q matrix. Okay. So let's look at an example of how we are calculating all these parameters like Q matrix, how Q matrix is assigned, how A and B is calculated in the Octave software, and how using A we can check whether system is stable, what is the eigenvalue, what are the comments on controllability and stabilizability. Okay, over to you, Kurtarth.
Okay, sure.
Great.
So I'll start to share my screen. Okay, so I hope the Octave screen is visible, and I'm showing a script. Basically, the software that we use, either Octave, Matlab, Scilab, any of these, they are mathematical computation software. We are just doing all the linear algebra related to this via a script, so it makes the task automated and easier for us. Okay, now we have just taken an example over here of a self-balancing robot by considering the system's A, B, C, D matrices that you have seen the derivation for, and we have fed the values of mass, length, in a moment of inertia, and everything for an example self-balancing robot that we have. So this is how the A and B matrices would look like, something where there are zero terms corresponding to the zero values in the Jacobian for A and B, and the calculated values of k1, k2, all the constants. Now, we saw that there's a controllability matrix which tells us whether the system is controllable or not by assessing the rank of the matrix, right, of controllability matrix. So to calculate that, there's a function CTRB in Octave, same in Matlab, where you can get the controllability matrix, and then by finding the rank of that controllability matrix, we can see whether the system is full rank system, basically controllable system, or not. And even if the system comes as rank deficient system, which means it's not a full rank system, still it should at least be stabilizable to be able to achieve our desired regulation in the system. So for that, we'll see if the system is stabilizable or not. So all these properties
we'll see. Now A, B, C, D matrix, you can see over here, we have taken C and D as unity. Now there was a question in chat why we take C as unity and D as 0. The reason is the output of the system is represented by C matrix. This is the relation of input and output of the system. So over here, the output of the system are basically the states, exact states that we showed. So X matrix, if it multiplies to this one, since this is a unity matrix, the same states will be reflected in output, which we want in our physical system. So that's why this is the correct representation of C matrix. So we want to measure all the states of the system, and since that is possible physically, we want to represent that mathematically as a unit matrix, identity matrix relation. Okay. Now Q and R matrix. These are the values that we have to choose to make our system optimal for the given performance that we want. So the performance that we want is giving a high priority on theta c, which means we should give some value which is higher to theta c, the highest value to theta c, which gives a higher priority in regulating theta c. Second highest priority to theta c dot. So we have given a slightly less number 3 to that. W dot is wheels angular velocity. We are giving it third priority, and the last one to theta W. This is an example Q matrix. We can tune it further. Now energy cost, we are giving it 1 right now, because in over here we are considering that we are giving all the energy to the single input system. If there would be two different inputs, over here we have only motors which are calculated theta W basically, to which we are giving all the energy. If there would be multiple inputs to the system, we'll be dividing the energies between the inputs. So over here, that's why this is 1. Okay. Now the SS function over here that we're using gives a state space representation of a system by getting the ABCD matrix that we defined for it, and discretization step that we saw. So now this is the step we'll need for using our system for deploying it in on a microcontroller or any processor. So since that runs on a discrete clock cycles and discrete execution time it has for every control calculation. So for that, we choose a sampling time of 0.01 second over here. We feed it into the C2D function of Octave, and this gives us a discretized system by applying Z transform to the time domain system, continuous time domain system. So this will give us a discrete domain representation of the same state space equations, and then we apply the LQR control. So by using the DLQR function, which is discrete LQR, similarly there is a continuous time domain LQR function which will take in the system, the Q and R matrices, and produce the gains corresponding to each of the states of our system. So we'll quickly see how this goes, and we'll see the other part of it after the execution. Okay, so as we run it, we can see something on the command window. The results will be produced on the command window. We see the A and B matrices. Now next we printed the rank. After A and B matrices, we have printed the rank of controllability matrix, which here as you see comes as 4. This means that the system is full rank system and it is controllable, right? After that, what you see is the eigenvalues of A matrix. Now, what does the eigenvalue of A matrix represent? We see there are 4 eigenvalues corresponding to 4 states, and 2 of them are 0, which are at the origin, and other 2 are splitted, one on the right half of the complex plane and one on the left half of the complex plane, which means one eigenvalue is in the stable region, one is still in the unstable region, which makes our system a unstable system. Now, after defining the system, we can see this is the state space equations: A matrix, B matrix, same as we provided, C and D. This is the continuous time model. Now, if when we discretize it, it will apply as a transform and the matrices will change since this is in discrete domain. Now, after we discretize it, we can observe something which is eigenvalues. So after discretizing it, if you see eigenvalues of this discrete system are different. Eigenvalues of continuous domain system where 0, 0, something in positive side, something negative side. Over here you see these are 1, 1, 1 point something and 0 point something. Physically, it is representing the same system, but since this is the Z domain representation, the unit circle is our reference for considering if the system is stable or not. So the two poles that were at the origin are represented by two poles on the unit circle, which represents a marginally stable behavior. Now the one that was outside or on the right half of the complex plane in S domain is outside of the unit circle 1.0874 in this discretized system, and the one which was in stable region is inside the unit circle 0.9196. So these are the eigenvalues of the system, and this is how we could judge if the system is stable or not in Z domain. Same we'll see after applying a controller if the system's eigenvalues are shifted to stable region or not. Before that, let's see what the controller gives us. So the K discrete you see over here is the result of applying LQR control on this discretized system. And you see there are 4 gains corresponding to 4 states. Since this is a state feedback controller, we'll multiply these gains to states and the rate of change of them. So 0.06 minus 6 minus something, the sign uh, is it doesn't matter right now for us because it will correspond to the hardware's sign convention of measurement and everything, so that can be scaled or inverted with respectively. Okay, next what we did, we want to check if the system is stabilizable or observable, controllable or not. So if you see, sysd is the discretized system. If we ask if it is controllable or not, the software calculates controllability and says it's controllable. Now observable, if we ask is it's observable or not, it says the system is observable, which means we can observe changes in all the 4 states of the system. Stabilizable also gives a true result, which means it is stabilizable. So this is the least condition that should be satisfied for us to be able to control it, stabilize it. Now, is the system stable inherently? The answer is 0, which means false. Since this is uncontrolled system, sysd is uncontrolled system, it gives false. Okay. Now, after applying LQR control, we got some gains. Now, how to use that gains, which we can represent as u equal to kx or minus kx. Now, as I said, these gains are represented by K matrix. X is the states. So when we multiply those gains with the states, this is the resultant output that we should fit to our system. So we represent it by U. Now in our state space representation, you have seen x dot equal to ax plus bu, which means this U should multiply to B matrix. And by multiplying it to B matrix, what we get is that B into U equal to B into kx minus bkx, right? Similarly, the same thing will feed inside the x dot equal to ax plus bu equation, and so this is what we get: x dot equal to ax minus bkx. And after taking the x out, what we get is x dot equals to x into bracket a minus bk. So this x and this x are the same, but the multiplication matrix, the coefficient matrix that goes with the x, previously it was a. This is the new matrix a minus bk, which means we got a new a matrix which will represent as as, and which is denoted by a minus bk. So this is the new a matrix that is applied to the states, and this is what will uh, use to define a new state space system, which is after applying the LQR controller. So the ABCD matrix of the new state space system will be AS. This is after applying the LQR gains, B, C, and D. And now the new state space system that we get is a system after applying LQR control, which means it should be stable. So let's check if it is controllable, it is stable or not. So the system we represented by sys2, and if we see over here, this system is stable. The stable function over here gives a true result for that. And if we see now the eigenvalue of that system, eigenvalue of sys2, these all are in. Now this is a continuous domain representation of the output system after applying LQR control. All the poles eigenvalues are on the left half of the complex plane. There are some imaginary parameters, but still the real part of it is on the left half of the complex plane, which means this is a stable system. Now if we see what response of the system looks like when giving an impulse, which means a disturbance to the system, and this is how the response looks like. If you see this graph, there are 4 plots shown: y1, y2, y3, y4, and the x-axis is time, which means how the states are changing with time when we give a disturbance is represented over here. Y1 was, I'll open the state sequence parallelly, and so we can see that. So first y1 is corresponding to the first state, which is w, theta w. Y2 is corresponding to theta c. So if we see when we give a disturbance, theta c is stabilizing again to 0, which is its equilibrium point. Theta w, y1, was deviated for a while, which we know that the robot has to, the wheels has to move to, in order to correct the tilt that the robot will get due to the disturbance, and this is represented, but still it's getting stabilized over time due to the LQR controller. And y3 and y4 are the velocity plots respectively. So this is how we should use the state space representations and mathematical software like this to apply LQR control. Now changing the value of these Q and R matrices will result into a different kind of response. It would be a faster or slower response, and the state which we give the highest priority will be corrected more rigorously. So that's how these things should be tweaked. Okay, I hope till now this is clear. So now these gains, whatever we get k discrete, should directly be used inside the microcontroller where we are actually applying it on hardware. Okay, okay. Switch over to our session. Over to you, sir.
Okay, so we have understood how the what is K matrix. K matrix is the final outcome of the all the mathematics that is done and all the calculation done through LQR while while implementing the LQR controller. So this is the final output. At the end, we get a gain matrix, that is K matrix, and each element of the gain matrix is corresponding to one element of the state matrix. Okay, and here u is equal to minus kx. So u is the input that is going to be implemented to the motor. Okay, so what u is calculated by this method. And you can see U equal to K1W, K2 theta C, K1 theta W, K2 theta C, K3 theta W dot, K4 theta C dot. This is the equation that we are going to implement in the hardware itself. Okay, this is going to be part of the code itself. Okay, now yeah, before we okay. So moving on to hardware. So we have so far understood why what are two different methods of controller implementation. One is PID, one is LQR. In PID, we don't immediately need to calculate the state space matrix of the system. However, it is good to know what is the system's behavior. Even if you don't implement LQR controller, you will at least know the properties of the system, whether it is stabilizable, whether it is controllable or not. This because if system is not controllable, stabilizable, no matter how much PID tuning you do, it won't be able to balance. Okay. So although in PID controller, system is treated as a black box, but if you do mathematical modeling, it will help you in assessing the nature of the system. And since you have done the mathematical modeling, it is rather easier to implement the LQR controller. Why we want to implement LQR controller? Because if you have ever tried to tune a PID controller, you must remember that if you change KP parameter, KP gain, you will have to definitely do some tweaking in KD and KI also. Okay. So all these parameters, although we represent them very separately in P as P, I and D, as P, I and D, yet they all are intertwined with each other. So if we change KP, KI and KD must be tweaked a little. And that is where a hit and trial game starts. But in LQR controller, we can directly tune the Q matrix, which tells the system that, okay, this is the state dearest to me and get me a new K matrix, which will only change the behavior of the system, focusing on that state only. So here you can individually individually tune the K matrix by individually intervening the values of Q matrix. Okay. So you are not directly changing something into K matrix, but the way you change Q matrix, the new K matrix will come in such a way that only that parameter is affected. Okay. So this way, it's more calculated and more uh, mathematical approach. So once we have all these K matrix and Q matrix and everything in place, we need to implement that on hardware. So now let's move on to the hardware that we have built on our side. So we have shown you the images of the system. A second, I'll show you again. Yeah. So this is our cell balancing robot, two-wheel cell balancing robot. You can see there are various components to it. It has it has two wheels, two motors, one EY5 mega microcontroller board. It has potentiometers and encoder switch. It has a battery. It has a motor driver IC. It has a sensor also at the bottom of the chip. I'll show you this. So all these components come together and create this system. So we talk about some key elements of this system. So the first element that we are going to talk about is the sensor itself. Okay. Yeah. So key elements here are sensors, motors, and how they are communicating to the microcontroller in order to balance the whole system. The sensor that we are using is called GY87. It is a sensor module. It has different sensors like accelerometer, gyroscope, magnetometer, and a pressure sensor on it, on the single chip. And it communicates these sensor data to the microcontroller through a communication called I2C. Okay, there are various communication methods through which peripheral devices communicate to microcontroller. One is I2C, one is serial, one is SPI. Serial is the method through which we upload our program from laptop to the microcontroller. And we also use, you can see this LCD here, LED device. It uses the third communication method, that is SPI communication method. So you can read about them online. So let's talk more about the sensor that we are using. So this sensor encompasses where it is, yeah, two elements, accelerometer and gyroscope, which are of use for us for this experiment for now. So can you can take a guess what accelerometer and gyroscope measures? Actually, it is shown in the PPT. So accelerometer actually measures the linear acceleration of the body, and gyroscope measures the angular velocity of the body. Okay, so through these sensor values, we can do a little bit math and find out what is the orientation of the body, what is the angle of the body, what is the theta c. That is one of the important states that we want to measure. But the catch here is that the accelerometer and gyroscope values are not sufficient for this measurement independently. So what we do? We combine those accelerometer and gyroscope values through a filter called complementary filter. Okay, so we need to filter those values because the accelerometer and gyroscope readings come with certain disadvantage. Accelerometer data is highly noisy. However, in a long term process, it is very reliable. On the other hand, gyroscope value is very smooth, but it has a drifting effect in it. So it is very useful for a short term change, but for a long term change, gyroscope value are not very reliable. So what we do, we pass the accelerometer reading to low pass filter and gyroscope reading to the high pass filter, and later combine the angle calculated by individually accelerometer and gyroscope through a complementary filter. Okay, further. So through this, we measure theta of the body. Using accelerometer gyroscope, we measure the theta c. Using theta c, we can also calculate theta c dot. How? By simply taking the difference between the previous reading and the current reading. Okay, previous cycle, since it's a discrete system, it is repeating the whole process after every 10 millisecond. So whatever was the previous theta value minus the current theta value gives you the theta c dot. Now, so we have measured two state, theta c of the body, theta dot of the body. Okay, we have two more states to read, that is theta of the wheel and theta dot of the wheel. For that, we use the motors. Our motors that we are using, they are equipped with a quadrature encoder motor. A quadrature encoder. So what is a quadrature encoder? In a quadrature encoder, there are two IR sensor placed at a 90-degree phase shift, physical shift. And there is a rotating slotted disk between them. So every time a slot passes, each channel A and channel B, those two IR pairs, they generate pulses. So you can see here every time this disk is rotating, channel A is creating a pulse, channel B is creating a pulse. Okay, so every time the IR pair gets interrupted because of a slot passing through the sensor, it creates a pulse. Now you can clearly see that these pulses are at 90-degree phase shift to each other. So if one slot passes through both A and B, it will generate two separate pulses, two separate events at channel A and channel B. And since they are at 90-degree phase shift, you can see that this one pulse, these pairs of one pulse can be further divided into four separate conditions. One condition is where B is 0, A is 1. Next is B is 1, A is 1. Next B1, A0, and next A0, B0. And since they are placed at a physical phase shift, it's a fixed physical structure, this phase shift will always be there. So by observing the values of channel A and channel B pulses coming from the motor quadrature encoder, we can check how much the wheel is rotating. We can count these pulses, we can count these instances, and we can check how much the wheel is rotating. Okay. So let us say if we are just looking at the channel A. So for if the wheel, suppose the slotted disk inside the encoder, suppose it has 100 slot. So what will that mean? Every time the wheel will take complete turn, channel A will generate 100 pulses, right? And same thing will also happen for channel B. So this quadrature encoder can be used in three methods, that is single mode, double mode, and quad mode. The single mode means we are counting pulses coming from just one channel and dividing the 360-degree by that number of count. In second, quad mode, we are counting the rising and falling edge of the channel. So in single mode, only rising edge was used to count the pulses. In dual mode, both rising edge and falling edge of one channel can be used to calculate the events. Okay. So what will happen? For same one rotation in dual mode, we will have, instead of 100 events, we'll have 200 events. So that resolution gets further improved. Okay. So now we are dividing one whole rotation into 200 pieces. And in quad mode, there are four separate instances, 0, 1, 1, 0, 1, 1, 1, 0 between channel A and channel B for one single pulse. So what will happen if 100 pulses are being generated on channel A and channel B throughout one revolution, there will be 400 independent instances. Okay. That means now we can get 4 times the resolution compared to single mode. Okay. Here's an example. Suppose 250 slots are there. That means in single mode, one pulse will represent 1.4 degree rotation. And in dual mode, it will become 0.72 degree. And in quad mode, it will become 0.36 degree. So you see, by changing the mode of operation of the mode of the way that we read the quadrature encoder, we can change the accuracy of the reading. So now what are we reading? We are reading the theta W, theta of the wheel. Okay, so theta wheel we measured. Same thing we'll do just like the just like the body angle sensor. We will do the same thing for theta W also. We will subtract the theta W current and theta W previous to get the theta W dot. Okay. And all of this measurement that we are doing. So we are reading values from sensors, different sensors. All of this needs to occur at a fixed time period. That is called the sampling time. And the sampling time is implemented using the timer ISR. So in microcontroller, there is something called timer. These timers are responsible for counting these. By configuring these timers, you can tell the microcontroller that after certain period of time, you have to execute certain set of instructions. Those set of instructions are called interrupt service routines. And those interrupt service routine could be anything. So here, in our case, those service routine will be reading the values from the sensor and sending the signal to the motor as the output U. Okay. Now, so since we are talking about hardware, there is one very critical parameter that is called torque. So we need, while choosing the hardware, we need to understand that even if you design a controller, your motor should be able to withstand the torque requirement. So this can be very simply calculated by this formula. Torque required is equal to mgl sine theta c, sine theta, theta c. That means it will depend on mass of the body, acceleration and acceleration due to gravity, and L is the length of the length of the distance between center of the wheel to the center of the mass, and sine theta, sine component of the body angle. That means the greater the angle will become, the greater the torque requirement will be, or vice versa. The greater the torque available at the motor you have, the greater the recovery angle you can achieve. Okay. Yeah, these are some of the parameters of the tools that we are using. So let me tell you something about eWi-Fi Mega also. So we are using eWi-Fi Mega. It's a eYantra built microcontroller board where we have combined Atmega 25, the Arduino Mega board, which hosts Atmega 2560 with ESP32 into one single chipset. So what happens? This gives us a capacity to wirelessly program the controller and also implement implement IoT applications using the same board. So it's a good tool to explore. You can explore that through Intra website. And with that, we reach to the conclusion of our session on control system and basics of self-balancing robot design. Let me show you one more robot that we have here. This is, I'll stop the sharing the screen. This is one iteration, iteration of the direction wheel based self-balancing cycle. So what will happen? What used to happen if it tilts on this direction, it rotates like this and it will push back the system on this direction. It's a very commonly used tool in satellites to reorient them. Such satellites are usually equipped with 3 reaction wheels, and whenever they want to reorient their satellite, they just rotate those discs, and due to conservation of angular momentum, the whole system rotates and reorients. So same concept has been implemented on this to balance the cycle against the gravity. Okay, that is it from our side. Please feel free to ask any question, and we'll also share a quiz form. Over to the organizing team. Do they want to share anything? Deepa ma'am, Ruchi. Okay, referral code. Okay, we will share. Okay, so good news is there that a new edition of eYantra robotics competition is launched, and we'll share a referral code with you, and you can pass it on to your teammates and your fellow students, also your like fellow colleagues, and through this they can get a discount on the registration fees. So I'm sharing the referral code in the chat box. And that is it that is it from our side. We are signing off from YouTube now, and for online people present in the WebEx, you can ask questions if you want. We are here, and we have shared the link. We have shared the referral code for EYRC 2023 in the chat. We'll also share